Welcome to this digital learning series on fluidics for nuclear disassembly. I'm Jacqueline Beltz. Phaco machines have evolved over the last decades to provide unprecedented stability to the anterior chamber during cataract surgery. Fluidics are extremely important during nuclear disassembly, where we aim to remove the nucleus whilst protecting the corneal endothelial cells and posterior capsule. Understanding the physical principles during driving this technology of phaco allows us to optimise machine settings and safely avoid or manage problems as they are encountered during surgery. Phacodynamics relates to four dynamic concepts: irrigation, aspiration flow rate, vacuum, and ultrasonic power. All of these factors combine to allow followability, which is the way material is attracted to the phaco tip, held at the tip, emulsified at the tip and cleared through the tubing. Properly orchestrated phacodynamics will result in good followability and improve the efficiency and safety of nuclear disassembly. The basic principles of phacodynamics is that in order to achieve anterior chamber stability during cataract surgery, we need to achieve a balance between the fluid that flows into the eye and the fluid that flows out. The fluid that flows in originates from the irrigation bottle and travels into the eye via plastic tubing and the phaco needle. The inflow may result from a pressure gradient, i.e. the bottle height, or by an infusion pump that will maintain a preset intraocular pressure during surgery. Outflow is the fluid that leaves the anterior chamber. In an ideal setting, with a closed chamber, this will be controlled entirely by the aspiration rate of the machine, but it will be increased or unbalanced if there is wound leak. If the inflow and outflow are balanced, constant anterior chamber pressure will be maintained. If the balance is off and consequently pressure is too low, shallowing of the anterior chamber might occur, leading to trampoline of the iris and possible posterior capsule rupture. If the balance is off, resulting in pressure that is too high, followability will be poor and also aqueous misdirection or deepening of the anterior chamber might occur, resulting in zonular loss. Proper management of the fluidics during nuclear disassembly will improve both safety and efficiency of surgery. Aspiration flow rate is the volume of fluid, which includes lens fragments, flowing through the tubing back to the machine at any given time. This is usually expressed in cubic centimetres per minute. The pump is the part of the phaco machine that brings fluid back via the tubing. The pump settings control the aspiration flow rate. The two main types of pumps in phaco systems are flow pumps, otherwise known as peristaltic, and vacuum pumps, known as venturi. Hybrid systems also do exist. Flow pumps, which are peristaltic, allow for independent control of aspiration rate and vacuum. Vacuum is created by compression of the tubing by rollers. This compression moves fluid through the tubing, creating vacuum. The vacuum is controlled by the amount of time the rollers run over the tubing when occluded. In a peristaltic system, the phaco tip needs to be occluded to build vacuum. A vacuum pump, or venturi pump, allows direct control of vacuum level. The flow is a result of and dependent upon the vacuum level, and a preset vacuum level can be obtained without occlusion of the phaco tip. Vacuum is measured in millimetres of mercury and is the difference in fluid pressure between two points. It's a negative pressure and determines how well nuclear material will be held to the phaco tip. Peristaltic pump systems include the Alcon Infinity, Alcon Centurion, AMO Sovereign and the AMO Signature. Venturi-based systems available today include the Borchelon Stellaris, the Borchelon Millennium and the AMO Signature, which has both pumps included. Some terminology that's important to understand includes compliance, surge and rise time. Compliance relates to how much the tubing will collapse as force is applied. This has an effect on the degree of vacuum possible and the level of post-occlusion surge. Surge is a phenomenon that occurs when vacuum in the line has been created due to an occlusion, but that occlusion breaks. Fluid then rushes from the high pressure environment in the AC to the low pressure environment in the tubing, leading to a sudden shallowing of the anterior chamber. Surge can also be described as a fluidic imbalance that occurs when outflow exceeds inflow. When surge occurs, you see the characteristic mini collapse of the anterior chamber. movement of the posterior capsule, and iris flutter or jump. Post-occlusion surge can be avoided by not setting the vacuum or aspiration flow rate too high, not setting the irrigation too low, and by anticipating the break in occlusion. Rise time is the time it takes for the vacuum to build in any given system. The foot pedal allows a means of control of the dynamics of the phaco machine. An understanding of this is therefore very important. The foot pedal has 4 positions. Position 0, nothing's happening, or it's turned off. Position 1, the irrigation flows into the eye. In position 2, the irrigation remains on. The pump begins to turn, so aspiration flow starts. Aspiration flow rate is preset. In a pump setting, if occlusion occurs, vacuum will start to build. In position 3, irrigation remains on, aspiration flow rate is at its maximum, and ultrasound starts. The range of each of the 4 settings is not equal. It's adjustable. In addition, foot pedal settings might be fixed or linear. Fixed is on or off. Linear builds via excursion of the foot switch until the programmed maximum preset value is reached. It's best to discuss your foot pedal settings with your company representative. The phaco tip is important in terms of the size of the actual needle and the sleeve, as well as the shape and angle of the tip. It's important that the sleeve matches the incision to avoid leak and allow a closed chamber. A 19 gauge tip might be appropriate for a 2.8 to 3.2 millimeter incision. A 20 gauge would be suitable for a 2.2 to 2.8 millimeter incision, and a 21 gauge for sub 2.2 millimeter incisions. The tip angle can be 15, 30 or 45 degrees and will depend on your preference and surgical technique. The shape of the tip can be angled, which is called a Kelman tip, straight or flared. The phaco tip has 3 main roles: a jackhammer effect, cavitation, and as a flow restrictor. The shape and size will impact the fluidics and the power of the ultrasound, and suitability will depend on your technique of choice and preference. Phaco machines deliver ultrasound energy into the eye to break up the cataract to facilitate emulsification and aspiration. It does this by vibrating the tip at a fixed frequency when the foot pedal is in position 3. Frequency relates to how fast the phaco tip oscillates back and forth. Usually between 27,000 and 60,000 strokes per second is efficient for nuclear emulsification. The lower the frequency, the less efficient the ultrasound will be. The higher the frequency, the more heat will be generated. Ultrasound power is calculated by the frequency of tip movement plus the stroke length, which is the distance the tip moves back and forth. Foot pedal control of ultrasound power is usually linear. Depressing your foot further increases the ultrasound power by increasing the stroke length, not the frequency. The frequency remains fixed. Too much power increases the heat dissipation and endothelial cell loss. Too little power creates stress on the zonules and capsule. To emulsify the nucleus, there needs to be a balance between pull and push. Aspiration flow pulls material towards the phaco tip. Ultrasound movement pushes it away. The vacuum holds fragments on the tip. A balance between all of this is crucial for efficiency. Different modes are possible to modulate this ultrasound energy. In pulse mode, energy is delivered in packets of predetermined on and off time. Pulse allows fluidics to work between pulses and allows heat to dissipate. This leads to better followability and less chatter. The duty cycle is the ratio of on time to total cycle time. Burst mode is also an energy modularity, but the period of off time is variable and can be adjusted. Longitudinal phaco is where the phaco tip moves forward and backwards. Torsional phaco is where the phaco tip moves side to side in addition to forward and back. Intelligent phaco allows a measure of back and forth phaco energy when a certain vacuum threshold is reached. This helps to clear clogs without the surgeon needing to do anything. Advances in phaco machine technology are allowing adaptive and adjustable systems that allow automation of nuclear disassembly. All of this progress allows improved anterior chamber stability for all different techniques and surgeons. Technology is definitely making us better surgeons. Efficiency, control, performance, energy reduction, reducing turbulence, allowing flexibility of techniques, all translates to improved patient outcomes. I would suggest meeting with your company representative to create your own personalised settings for the machine that you use, and to make sure that you know when, why, and how to adjust those presets when necessary. In addition to discussing Phacodynamics with your students, mentors, colleagues, and company representative, I would recommend that you choose and read at least one reference text. I've found those listed here to be quite useful, although do bear in mind that this technology is changing super quickly. It's so exciting and quite hard to keep up.